Hello everyone and welcome to the solutions video for education round 123. This went pretty good for me considering I've been dropping for so many contests, so no complaints so far unless I FST again. But that being said, I'll be explaining solutions for A to E. And so let's get started. But before that, make sure to subscribe. Okay, so problem A. In this problem, we have three colored doors, red, green, and blue, and their keys, red, green, and blue. So we go from left to right, and what we have to tell is if we will be able to open the doors. How we are able to open the door is if we collect the key before reaching the door. So we just have to check that red key occurs before red door, green key occurs before green door, and blue key occurs before blue door. So that's what I've done. Let's have a look. I input the string, create a map for index, and store those index, and then I'm checking red key before red door, green key before green door, blue key before blue door. If so, yes, otherwise no. Okay, not this, yeah, here. So problem B, what does this problem say? We want to generate an anti-Fibonacci series of basically permutations. So 1 2 3 4 5 6, we are given some value n, and we have to reorder this permutation of 1 to n such that it is anti-Fibonacci. And what is anti-Fibonacci is that ai minus 1 plus ai minus 2 is never equals to ai for all I less than n minus 1, right? So sorry, for all I greater than 2. So basically for any three consecutive numbers, they should not satisfy the Fibonacci property. So how do we generate these permutations? And we have to generate n of these. So let's look at the normal permutation 1 2 3 4 5 up to n. Here notice that the sum of two numbers will always be greater than the next consecutive number except for this scenario. So their relative ordering can just be whatever, and so it cannot be just whatever, but so if it is like this 4 to n, then they will satisfy, but this won't satisfy because 3 equals to 1 plus 2. So we just have to make sure this does not happen. So how do we make sure of that is we can try 1 3 2 or 3 1 2 and 3 2 1. Okay, so if n was 3, these are the three permutations that we want. But what about bigger ones? So notice that all we want to do is not have 3 after 1 and 2. So one way is to have it like have the permutations be like this up to n. This is anti-Fibonacci because 1 plus 2 is not 4, and then further also it satisfies the property. And if you rotate it with the 3 fixed, basically you write it like this n 1 2 3 n minus 1. This also satisfies the property because this part is decreasing and the other part is increasing like normal, so both won't satisfy. And this way, so if you keep rotating, the next would be n minus 1 n 1 2 n minus 2. So this will give us n minus 1 permutations. The last permutation, how you can get that is you can take inspiration from here. You write 1 here, then 3, and then write the remaining 5 6 n. So it was a pretty stupid constructive in my opinion. Maybe it had a much neater solution, but who cares, this works. So let me show you my implementation. I used a DQ. It wasn't really necessary. You could have just used I used DQ because I wanted to rotate, so rotation is easier there. So I have this, I take input n, and now what I do is I do not put 3 in the DQ, because I can just manually output this and have a rotating array here, and this time I manually output 1 3 and then output this. So this is what I'm doing. So this case I'm outputting first of all here. So first of all I'm outputting answer 0 and 3, so that is 1 space 3, and then I go from the remaining elements, that is 2 4 5 6, and print them. And then what I do is n minus 1 times I rotate it. So I print 3, print the array, and then I rotate it. So get the element from the back and remove it, put it in the front. That's why I use DQ for easy rotation. So that was it. Pretty simple, I guess. I really think there has to be a more neater solution, but I don't have that for now. Okay, problem C. This was a good problem. So here we have an array. It can have negative elements, and what we have to do is, for a given k, we have to add x. So x is also some positive value. We have to add this value x in exactly k unique elements and then tell the maximum subarray sum. So the one for which you use Cardano's algorithm. So, and what this k is, actually you have to tell for every k from 0 to n. So how do you tell that? So for k equals to 0, the array does not change, so that is the maximum. For k equals to 1, what you have in options is actually you can just take x, whatever the previous answer was, plus x. So basically after that, so let's consider some midpoint. Okay, so let's take 5. So how do we tell for k equals to 5? K equals to 1 was a bad example, that's why I discarded it. So for k equals to 5, I have a1, a2, and an here, right? So which subarray should I choose where I'm changing 5 elements to have plus equals to x? Now what we should do is take the biggest, or is we take the subarray which has the highest sum, not the biggest sum, the highest sum, and then add 5 times x, because we can just increment 5 of those elements, except for those subarrays which have less than 5 elements in it. Maybe the array is like 9, 30, minus 1, minus 2, minus 3, minus 4. Here notice that the maximum subarray sum is 39, but for k equals to 5, we need, first of all, for k equals to 5, we cannot really, add all these 5 into this. And why so? Well, that is because there are only 2 elements. So what we do is, we do consider this as a possible option, but what we can also consider is take array of 5 elements and add x to all those 5 elements. So basically what I'm saying is, the subarray with highest sum without any alteration could be some array of length 2 3, and so it can only get so many increments in the elements. So what we have to do is consider the subarrays of different lengths as well. And because n is only 5000, what we can do is we can store all the sums somewhere, and this is how we proceed. Okay, so let me take this. So for, let's say you have calculated for k equals to 4. Now how do you calculate for k equals to 5? Now for k equals to 5, obviously k equals to 4 could be an option, because whatever we chose for k equals to 4, we can choose for k equals to 5 as well. It's just that we will increment some random number not in the consideration to satisfy incrementing k elements. Okay, so now for k equals to 5, how do we find this? Well, now what we can do is consider all the subarrays of length greater than equals to 5, and among them whichever has the greatest sum, to it we add 5 times x, because all of them will be able to have at least 5 elements, so we can always increment its sum by 5 times x. So the answer for 5 is maximum of, answer for 4, and answer and the maximum subarray sum for greater than equals to 5 length plus 5 times x. So that is it. Basically, why we need to consider them is because, like I said, take this example again. For 4, our maximum subarray sum with x equals to, let's say, 5. Let me just take all of them to be -1. So for k equals to 4, our best choice would be to take this subarray and add all the 4 elements. And for the next one, it would be to take one more, even though without having that ability to add x to one more number, choosing this won't be optimal. So that's why we also have to consider the suboptimal subarrays to get to the optimal answer. So let me show you how I did it. So because n is only 5000, we can do an n square algorithm. So since we care about the sum of the subarray sum and also its length, what I'm going to do is store for every length what is the maximum subarray sum. So here I'm going from, so yeah, this is the input, and then I'm doing a subarray iteration. So from I0 to n, j I to n, I'm getting the sum of that subarray, so that's why I'm storing sum. So if it is like a1, a2, a3, an, I go from here, then this. So it's like a double pointer. It is a double pointer. And now what I do is, so for whichever subarray I'm considering right now, for every ij pair, I'm getting what the length of this subarray is, and m sum represents the maximum sum for given length of subarray. So I store that, and previous is just the maximum over all of these subarrays for now, and then I store a suffix maximum. It's not suffix sum, it is actually suffix maximum of this maximum sum array, because remember what we needed is the maximum sum for subarrays greater than equals to 5 length. So that's what I'm going to do. So for k from 0 to n, the current answer would be obviously the maximum of previous answer and what the suffix maximum is up to this. So because I'm storing this previous over here, yeah, actually never mind, I didn't need to store it here. So anyways, so suffix sum for 0, it's not suffix sum, it is suffix maximum sum for 0 would just be the output that Kadani's algorithm gives us. It's just calculated via brute force, and count would be 0, so I will get that, and then I'll store it in previous. And now next time I will consider for array lengths 1. So let me give you this example. If everything is negative, right, then for k equals to 0, our sum is 0 because I cannot increment anything, but and x is, let's say, 5. But for k equals to 1, I can increment something and make it +4, and then that would be my best array. And that is why I have to consider subarrays of length 1 as well, because if I were to just consider the best subarray sum, it might not have enough elements to take the full advantage of this So that was this. Now let's move to problem D. Cross coloring. Okay, so in this problem we are given an array, sorry, not an array, I'm so used to it. So we are given a matrix, and let's see what we have here. Yeah, n m, and there are k colors. Initially everything is white, there are k colors, and then we are given q coloring, so q actions basically. So what we are doing is, for the actions are like this: I1, I2, sorry, J1, I2, J2, IQ, JQ. So in the first action, what we are doing is we are selecting I1 J1 grid. So let's say this is the grid that we are selecting, and now it is up to us what color from 1 to k we want to choose, and we will color every every cell in its column and its row to that chosen color, and we keep doing this over and over again. So let's say I color with color 1, so this is the color right now, and then let's say I2 J2 is over here, and now I color with 2, so this would get overridden. It would become like this. So as you can see, depending upon which colors we choose at every step, so these action positions we are given IJ, but we can choose our colors, and based on which color we choose, we can get a different final configuration. And what a configuration is, obviously just the coloring of this board or a grid. Now what we want to tell is how many different colorings of this grid we can get by choosing colors from 1 to k at all these positions. So first of all, let's see how we will do it in a trivial case. So let's say something like this. So once it happened here, so this is the first time and this the second time. So this covers this and this covers this. Now we have k options to color here and k options to color here. So k square would be the total final configurations, right? So is it just k multiplied by k up multiplied by q times, so k to the power q? Well, no, because what happens to some of these colorings is they get completely overlapped. So let's say you once tried this. Okay, so this was colored like this. Now next time you colored here, so this entire thing got colored. So see, this got overridden and this got overridden. The next time maybe this got colored and this got overridden and this got overridden, and then maybe next time this was colored, so these two got overridden, all these three got overridden, and this got overridden. So everything of that black has been overridden. So what color we choose in it does not affect our final configuration. So we just have to figure out which of the colors will get completely overlapped by succeeding colors, succeeding colorings or whatever, and those we won't count. So we will count only the influential ones, only the effective ones, and let's say it is count, so the answer would be k to the power count. And obviously we have to do modular exponentiation here. If you don't know what that is, CP algorithms is your best friend. It is basically like finding this in O log count n with modulo some value. So this is not in the time complexity, this is in the value. So we want to find k to the power count modulo m in O log count. That is what binary exponentiation is. Okay, so how do we know if some cell has been completely overlapped. Let's look at, okay, I'm not gonna use blue, let's use black. So let's have a look at this grid. And let's say we are considering if this one will be overlapped by its succeeding colorings. So what should be satisfied in order for this to happen? Well, somewhere in the future or after this, we want an operation to share a common row, maybe, right? So if it shares a common row, like let's say here, right? So it will override everything here. And if something shares a same column, so like here, it will override everything here. So this much is enough. It is not sufficient, but this much is enough. And so if the column and row in which this point exists, if this was already done, then we don't have to consider it, because it won't have any effect. It will be completely overlapped. Okay then. So, but there are other cases as well, and let's look at them. Is there obviously one case that if somewhere in the future we color this again, so then it would get removed? And what is the next case? Well, what if every column was colored, right? So what if every column like this was colored? Then obviously every row would also be colored, right? Or if every row was colored, then every column would have also been colored. So these are the things that we have to consider. And now, because we have to consider what happens in the future, we can process it from back, because if we already know what will be colored in the future, then we can figure out if we need to color this or not. So let's store a set of all the rows that were colored and all the columns that were colored. Okay, so if its row was colored and its column was colored, then it is not necessary to use it. It is an ineffective coloring. So row colored and column colored. Or if all columns colored, or if all rows are colored. So either this condition is required, this or this. So we iterate from back and see if either of these satisfies, then that means coloring it is not useful. We do not consider it. Otherwise, we insert its row into our set of rows and its column into our set of columns, because those are what are colored. So let's look at the implementation. How many people did it, by the way? Yeah, a lot of people. I'm guessing most people will want to see editorial for this only. Maybe C as well. I don't know. Okay, so take the input. If you don't know how this works, check out my template video. And then set for rows and columns. Count is what are the effective colorings. We go from the back, get the current row and column. Now you can either do it like this, or I'm just checking is row colored and is column colored. So row will be colored if row already existed or all columns were colored, and column would be colored if column already existed and all the rows were colored. And if both were colored, both row and column were colored, then we can just skip through it. Otherwise, increase the count of effective colorings and add its Ri and Ci in our sets. And finally, just find the modular exponentiation of k to the power count, mod this value. Okay, problem E. Now I overcomplicated it a lot, but it was actually very simple. Let's discuss. So we have a rather big grid. So like n can be up to 1e8. Okay, so obviously we cannot have the grid in memory, and then we are given a bunch of operations, basically how we can walk on it, or who is walking. Let me check. Yeah, so a robot is walking. It can only go right or down, and we are given a path that he had followed, so like something like this. Okay, so from here to here. And now what we can do is, so we are given the path string, right, r in r and d terms. Now what we can do is we can select some r or select some d, select some index basically, and duplicate it. So if you had d r r d d r, if you select this index, you will duplicate it. This is a new duplicate, and it would become like this. So if you were to look at it like this in the drawing, if you were to duplicate, so this is one operation, this is one operation, right? If you were to duplicate this operation, it will go there, and the remaining thing will remain same, right? And what we have to in the end find is basically we are allowed to do as much modification as we can. We just have to tell what are the total cells we can cover, not in one modification, basically of all the possible ways we can modify it. And on all those modifications, what are the cells covered, we have to tell the union of them. So that is what we have to find. Now let's analyze the operation. So this was one, this was one. If we were to do the duplication, as you can see, it kind of translated. If I did it again, it would just translate again. So there's mostly translation. And if I were to move this, if I were to move, so this is one, right? If I were to move this here, it would get translated like this, right? So this is what's happening in an operation. And how much can I move it? Well, that depends on the last position of the element, right? Like where we are in the final, because we can only duplicate, we cannot remove any element. So what's happening, if we could remove, then we could always cover everything. Or would we? I'm not sure. Probably, yeah, then we would be able to cover everything. But we cannot do that. So here, notice that no matter where I do the operations, right, I'll only be allowed to move 1, 2, 3 in the right and 1 in the downwards direction. So now consider this segment. Okay, so since this can go 3 right and 1 down, it will cover this much. This will cover this much. So everything is, this much is covered. What will this be able to cover? Well, this line segment, it will go right, but it going right won't really do anything. It will only move 1 down and cover this much. Now for this vertical line going downwards is not really gonna do anything, because whatever it will cover will be covered by this. But going to the right will help. And how much it can move? 3. So 1, 2, 3, 1, 2, 3. So as you can see, every segment, so except this final segment, every segment moves only perpendicular to its orientation. And how much it moves, depending on that, depends on the position of this point, right? Except the last one, obviously, right? So this can only move in the right. Okay, so this can only move in the right, or if it is down, it can only move in the down. And how much, again, that is decided by this. And finally, if there were no elements, so that is an edge case. Basically consider this right? If this was the movement that is in the initial movements, then it can just go up to the length but not really anywhere else. So that is about it. So for this case, obviously we can, depending on the orientation, when there is only one line segment, depending on the orientation, actually it doesn't even depend on the orientation, it will always be able to go in because it's a square grid. However, if it is not, it will be able to go how much? How much do you think it will be able to go? Well, actually, so like we say, I just said that it will be able to go here, but remember, I also said that things are only able to move perpendicular because uh, whatever this movement happens, right? Whatever this movement happens, this was actually covered already by this, so this doesn't happen. And because it cannot really move perpendicular, because how will it move perpendicularly? It needs something before it to move perpendicularly. It won't actually move. So what this covers is its length. If there was more than one segment, if there was one segment, then it covers n. Okay, so the first segment behaves differently and the last segment behaves differently. It covers the square entire in the left and right direction, but the other ones, just depending on their orientation, they move perpendicularly. And why do they move perpendicularly? You can easily visualize it. This moves so that this moves perpendicularly. It's really hard to draw. So that's basically it. Let me show you the implementation. So I created a line structure to store the x1, y1, i1, j1 and i2, j2 of the line. And then I iterate on the line and I'm basically storing two positions. So let's say this is a line segment, right? Going from here to here. So I'm storing this and this element and this element. Okay. So the first and the last element is what I'm storing. So this is basically, as long as there's a repetition in the elements, I move to store the line segment. And now there are plenty of unnecessary variables here because I was overcomplicating it, but let's see. So this is for the last element, and if m is greater than 1, obviously what we do is, how much are we able to move? We are able to move this much, right? This much and this much by this. So we have to consider this width and this height. This is getting actually messy. So basically we have to consider this width and this height. So that's what I'm calculating here. Get the width and height, add that to the answer, and then what you're seeing here is absolutely useless. Now for the middle elements, I'm getting their delta in height and delta in width. So if there's delta in height, that means it's a vertical one. So in that case, what MW is basically movement in width and H is movement in height. So movement in width versus delta in height. So if you look at this one, right? So let's look at this one. So this moves perpendicular to its length, right? So since it is dw, what I do is movement in height, which was this value, multiplied by its width, and the opposite for dh. This and this is unnecessary because I was doing something else. And then finally, for the first element, if there are more than one element, then it doesn't really move. So it only covers what it initially covered. Otherwise, it covers n elements. So implementation is not the best. I mean, if I remove the unnecessary part, implementation would be good. But that's about it. It wasn't really a tough problem, I think. I just overcomplicated it, saying it for the 10th time because I'm sad about that. Well, anyways, that was the solutions. Hope you enjoyed. And with that said, bye.